So if we look at the graph, which should be a bunch of straight lines, that depicts somebody's motion, okay, somebody's change in position as a function of time, all right, we're actually seeing a variety of velocities here, okay? This is actually mapping out someone's displacement, all right? So what it's telling us here is that from the starting point, right here, do they move in positive territory or negative territory? For the first 5 seconds, they're going to move in negative territory. All right? They're going to actually go further away from their target destination than their actual starting point. So it's like me saying that I want to walk from Traff down Simpson Street to Sherbrooke Street. That's my end destination. But first I'm going to cross the street, put something in the garbage can, and then come back across and then keep going down the street. Okay? So in reality, my end point is still where I want to go, but I will have covered more distance. We're not even going to be talking about distance here. First things first, what kind of line, what kind of slope am I seeing from the starting point, 0, 0, to the first stop, which would be here, okay, second stop here, and third stop here. So what am I seeing from the starting point to the first stop in terms of my position? Am I in positive territory or negative? Negative. Okay, so that means I'm going, my position is going to be, my displacement is negative. What does that say about my velocity? My velocity will be negative, okay? Now, what actually happens here from 5 seconds to 10 seconds? What happens from 5 seconds to 10 seconds? There is a pause. Do I have a velocity? No, I don't. Why? Because I have a horizontal line here, which states that my velocity is constant, okay? My velocity will be 0. So am I actually changing positions here? No, I'm not. I start from my starting point, I go backwards a wee bit, and I take a pause there for 5 seconds. And then after the 5 seconds is up again, you'll notice that I start to do what? I move in a forward direction, in a positive displacement, until 25 seconds where I come to rest. Does that make sense? Okay, now, when you look at a graph like this, okay, there's a lot of stuff going on here. All right? There's negative velocities, there's positive velocities, there's zero velocities, but there's also displacement and distance. Okay? What would be my overall displacement here? What is my final displacement? 1 meter, correct? What is my final distance? Why do you say 2?
Because you take the absolute value of.
Because we're taking the absolute value of our displacements. Okay? So from here to here, I'm actually traveling, or the object is actually traveling 0.5 meters. Even though it's in the negative direction, it is an absolute value. Okay? No distance is traveled here. And then we've got another absolute value. We've got another 0.5 meters here. And then we've got 1 meter from here to here. So the distance is the sum of all of those displacements. Whereas the overall displacement is from 0 to your actual final location. Okay? It doesn't take into account your backwards motion or your negative motion. Let's go back to our old example of Cecilia and Sydney's house. Okay? Let's say that Miss Lupel is at meetings, or no, not Miss Lupel because that's creepy. Let's say that Gabby is meeting friends at Collège de Montréal. Okay, we know that Collège de Montréal is in between Cecilia's house and Sydney's house. Let's say Gabby leaves Collège de Montréal, has to go back to Cecilia's house, pick her up, and she walks at a constant rate. Then they hang out at Cecilia's house for a wee bit, have a glass of water, chit-chat. Then Cecilia grabs her stuff and they walk past Collège de Montréal, which is the starting point, and the end point is Sydney's house, a little bit down the street. Okay, that is what this is graphing. Forget about negative velocities here. Okay, what we're actually looking for in a position as a function of time graph is your actual displacement versus your distance covered. Okay, this graph is read differently than, let's say, a velocity over time graph. That's where it starts to get a little bit more complicated. Okay, but for a position of time graph, that is the type of scenario that we are graphing here. If I have 30 kilometers per hour, and I want to get that to meters per second. Okay, I've got two variables here, or two values that I'm going to have to convert. I'm going to have to convert my kilometers to meters and my hours to seconds. And I'm telling you right now, you need to show your work for your conversion. It is not enough for you to say 30 kilometers per hour is equal to blah meters per second. You've got to show me how you got that. That is worth a mark in any of those problems. And you will lose a mark if you don't show me that. Okay, you will also lose marks if you don't include units the whole way through. So if I want to do this, 30 kilometers per hour. Okay, I'm going to work on my kilometers first. And I'm going to say that in 1 kilometer, I've got how many meters? What's the equivalency? 1,000 meters, right? Well, look at this. If I'm multiplying these two, I can get rid of kilometers. I now have the right unit on top. Hours, I've got to bring that down to seconds. Okay? How many minutes are there in 1 hour? 60 minutes in that should be the other way around. Okay, 1 hour, because I want them to cancel out, is going to have 60 minutes in it. So these guys cancel out. I'm still not where I need to be. Okay, 1 minute has 60 seconds. Correct? These cancel out. I'm left with the right unit. So the way this works is you multiply everything that's on top of these fractions together, and you divide it by the multiplication of everything that's on the bottom. So in this case, it's going to be 30 times 1,000 meters divided by 60 times 60 seconds. Okay? Or you can always take, I will even accept as a form of work here, this is really showing your work. I will even accept if you sit here and you have 30 kilometers per hour multiplied by 1,000 meters over 3,600 seconds. I would accept that. Okay? If you show me that work, I will give you whatever the mark value is for that. Because it shows me that you're actually putting some thought into it. Okay? If we start to actually talk about the idea of the graphical representation of velocity as a function of time, I expect you to know how to actually make a graph of velocity as a function of time based on an object's position as a function of time. Okay, so if we go back to our adage here where we've got that graph from the first one, I've made it a little bit more condensed just to save space here. Okay, so you are finished at 20 and 1, so we will actually go up here. Okay, so this is my graph for kilometers per hour. Okay, so kilometers here instead of meters, hours instead of seconds. Same kind of concept applies. In this case, when we're graphing the velocity as a function of time here, from 0 to 5 hours, okay, they are traveling at a velocity of what? If you can mathematically calculate this velocity, you'll see that it's a velocity of a little over, I believe, 5 meters per second. It's probably about 6 or so, 5 kilometers per hour. So I think it's about 6 kilometers per hour. So if I want to actually make an equivalency here of a velocity as a function of time graph based on this position as a function of time graph, from 0 time to 5, my velocity, okay, is just a little bit above that. And then here, my velocity changes. Okay, so I go up to my equivalency here, and my velocity